disordered systems, non-interacting and interacting, not two phases. One is totally extended, so to say, ergodic extended, and the other is totally localized, but three different phases in which there is also an intermediate phase which has very peculiar properties, and we call it extended but not ergodic state, non-ergodic extended state. I told you this is some simple calculation, that it is only possible in a situation where there is either some hierarchical lattice or hierarchical Hilbert space, like we suspect it is the case for many body situation, or there is a simple lattice or d-dimensional, and the hopping over this d-dimensional lattice, which is power law. So then, at the end of the day, we came to the problem how to characterize this new phase, if it exists, and we came to a notion of multifractal wave functions, and basically I told you that the simplest image of the multifractal wave function is that you cut your profile of psi squared at some level, and then ask a question, what is the map of the region where the wave function is above this level, and the answer is that the map is fractal. And then, more importantly and more formally, this multifractality of wave function means some specific distribution of the wave function coefficient, the wave function amplitude, and this distribution has the following form, where there is some function of the argument which we call alpha, and it contains the logarithm of psi, the argument of our distribution function, and then the logarithm of the system size. And what is important for this form is that this logarithm of the system size stays here in the argument in the denominator and in front of this function as well. And if it happens this way, if the distribution is like this, then you can compute the moment of the wave function IQ. You can compute it just by integration, and then you see that there is a big number here. So this integral, each of them, this is a normalization integral, and this is the integral which contains this power q of the wave function, and so we can do this integral by saddle point approximation, and saddle point approximation involves, of course, stationary point, saddle point, so you differentiate it with respect to alpha, and so you find, after evaluating this integral, you find the power law, and this power is expressed in terms of the derivative of this function. And this is famous Legendre transformation. So these two descriptions in terms of the distribution function and this f of alpha, and in terms of the moments, they are equivalent, and the relationship between the two things, tau of q and f of alpha, are given by Legendre transform. Now, the typical form of this function f of alpha is like this. So it has certain properties, and one of them, important property, is that it has a maximum, and the value at maximum is equal to 1, and one can easily show that this is a requirement of normalization of the distribution function, that the integral of the distribution function over logarithm psi is equal to 1, and this is translated in this maximum at 1. And then there is also a combination f of alpha minus alpha, and it should have the following form. It should be negative with maximum at 0. And this is another normalization, but this time is a normalization of wave function. This means that at q equal 1, I should have tau equal to 0. So there are two normalization of the distribution function and normalization of the wave function, and they are translated in these values of the maximum. So this is some general properties of this function. But now, in order to earn some intuition about this function, because it is a language which is used further on in order to compare different multifractal states. So first of all, let's consider the limiting cases, what happens to this generic function when we are in an ergodic state. What means an ergodic state? Ergodic state means that the wave function occupies total allowed volume or finite fraction of this volume, and then it is normalized, and it is also assumed that it doesn't fluctuate very widely apart from de Broglie wavelength. And so one can then easily say that the psi squared corresponding to such situation scales like n to minus 1, where n is the number of lattice sites here. So it is simply by normalization, because if it scales like 1 over n, then you sum over n and you have unity. So this means that the wave function which in this formalism, the wave function in this formalism is considered at the level n to minus alpha. I told you that what one has to do is to cut the profile of psi squared at a level which is parameterized by the variable alpha and the total number of sites. So psi squared is parameterized like n to minus alpha. And if all psi squared scale like 1 over n, this means that alpha takes only one value, and this means that such parabola-like function is actually degenerate to one line if we have an ergodic case. Now let's come to conventional localized case, and conventional localized case tells you that there is a region where the wave function is independent of the total number of sites, independent of the system size, and that means that it is of order n to 0. It doesn't depend on n. And this means the following. This means that f of alpha takes 0 value, which means 0 value means the following. As I said, the number of sites where the wave function is higher than this level is n to f of alpha. So if I have localized situation, this number doesn't depend on n, and therefore f of alpha is equal to 0. And as I said, alpha itself is also equal to 0. So this point corresponds, if we have f of alpha 0 at alpha equals 0, this signals about localization. So the localized function is always when f of alpha is 0 at alpha equals 0. But then conventional localization is exponential. And this means that since the wave function falls down and takes all the values down to exponentially small ones, this means that there are instances, there are some of order 1 number of points where it takes any value, and any exponentially small ones. And this means that, in fact, this f of alpha is an angle like this. So this point corresponds to localization, and this horizontal line corresponds to exponential localization. So there's no minimum value of the wave function. The minimum value is 0. As I said, the wave function has a property that it should have maximum, and it should be 1 at maximum. And here you can think of this f of alpha as an infinitely small slope, and this 1 is reached somewhere beyond this screen. So these are two degenerate cases, and a generic case, as I said, is like this. And how one should read, how one should make conclusion about the property of the wave function looking at f of alpha is very simple. So as I said, if f of alpha is equal to 0 at alpha equals 0, this is localization. Now, if there is a gap here, so this means that at alpha equals 0, f of alpha is very small, then it signals of extended state. So if it were localized, it would go like this, at least. Now, then, as I said, the ergodic case is when this f of alpha has 0 spread along the alpha. So it is just vertical line. So if it has finite spread, then it means that it is a broad distribution of psi squared, and this means that it is non-ergodic. So two actually features. The gap says that it is extended, and the finite spread says that it is non-ergodic. So and now we come to a particular example where we were looking for such multifractal state on a random regular graph. Why? Because this is statistically homogeneous system, but locally it is like a tree. So this is a good candidate to look for such state, and we did this work already in 2014. And so what happens is the following, that if disorder, which is disorder in the on-site energies, if disorder is very large, like here, then you see that the f of alpha has approximately a triangular form. It really reached 1 when it should be, but what is important is that it goes straight to 0 approximately in a linear way, and with some slope which is smaller than 1/2. But the important is that it hits 0. So f of 0 is 0. So this means that it is localization. Now you see that this localization is not like the conventional one. It is with some slope, and this is because of the following. This is very easy to understand, because if the wave function is exponentially localized, this means that it behaves like this. But what is R? R is the number of generations. So if you have a tree, then R is like a radial variable on the tree. So it is number of generations. But the total number of sites is exponential in the number of generations. And that's why if you plug it here, that R is logarithm of n divided by logarithm of the branching number, then you get a power law. So this psi squared is a power law. But as I told you, a power law which depends on the parameter, this power law means the following, that your wave function has a minimum value. So what I said is the following, that at an arbitrary distance from a given, from a root of the tree, of course this is an arbitrary value, so R is some running distance from the root of the tree. But if you want to ask a question, what is the minimum value, you should take maximum distance. And maximum distance is related to the total number of the sides. And therefore, psi squared has a minimum value, whereas exponential localization, for exponential localization, minimum value of psi squared is 0. And this is why this this line is horizontal, and here it is not, because if I have the minimum value, then then this means that this f of alpha has a cutoff somewhere which corresponds to this minimum value, and then one can show analytically that for the Betti lattice, the distribution function of psi squared in the insulating phase is power law, and as I said, power law is translated to a linear f of alpha, and so it is linear, but it must have some finite slope, because it reaches this maximum at a finite alpha, and then it is cut off. So this is, so to say, Betti insulator. So if you look at the pictures, then this would be the exponential localization on a normal lattice, so where the wave function is exponentially small far away. Then this would be a multifractal where there are valleys and peaks, and this would be the localization in with such f of alpha, so to say, Betti insulator, because there is the minimum value is not 0 but something, so you have some small background here. So this is a property of the Betti lattice, but this is not the one that I was especially looking for, because I was mostly interested in what happens not in the localization phase, which is simple, but what happens in the delocalized phase. And what we found here is the following, that as you increase disorder, then your f of alpha evolves in some continuous way. So it is first resembles a triangle with slope smaller than 1. Then it reaches slope equal to 1. And at that point, you still have localization, because this guy goes to 0 at alpha equal to 0. But then, as you further, and this is the critical point of the Anderson transition. This is how it looks like at the critical point of the Anderson transition. But then you increase your, then you make the disorder even smaller, and then the gap appears. So when the gap appears, as I said, this is an extended state. But this state is with some spread, finite spread. It is not like ergodic state, which is hypothetic ergodic state, which is shown here. What we found the following, that in the region where we are able to do calculations, because at very small disorder you need actually incredibly many realizations of disorder in order to suppress fluctuations, and therefore we could not go to very small disorder. But a disorder which is 2 times smaller than the critical point, it was still some finite spread, and we made a conclusion at that time that indeed we found this non-ergodic state. Moreover, we did not find the ergodic one. But of course, it could be that it is somewhere at even small disorder, which we at that time could not study. So at least we could say, well, we found this non-ergodic state. And now of course, you know, every numerical work, it has limitations, and the limitations is the following, that you have to somehow extrapolate to infinite sizes. Because the convergence is poor. This problem is very hard numerical problem, because the convergence is the inverse logarithm of the number of n, and therefore, even if you take, let's say, few 100,000 of sides and diagonalize such a matrix to find the distribution function and then to extract this f of alpha, it is still not enough to have a clear convergence. And therefore, we had to implement some extrapolation procedure, which I don't have time to speak about. But of course, people who don't believe in that, they can say, well, you do some extrapolation and you are not sure that it works all the way, and therefore this is just some indication, but of course not a proof. Then this is basically the other attempt. So this attempt was to find the f of alpha, which is another word for distribution function of psi squared. And the other, in fact, more traditional approach was to compute the fractal dimensions, because if you consider this moments, then you obtain some power law in the system size, and then this tau of Q, as I said before, one can define the fractal dimension that depends on Q in this way. So one has to compute the moments and then observe the power law, and then extract tau of Q, and then extract fractal dimension. So if you do this, then essentially for better convergence, you average the logarithm and not the value itself, because even the logarithm fluctuates very widely. So you average the logarithm, then you take the derivative with respect to the system size, and what you get would be the fractal dimension at Q equal 2, because here it is 4, if we would reach convergence. So if this guy would reach some asymptotic n-independent behavior. But in fact, as I said, the convergence is never reached. And so the asymptotic behavior, there is still some curvature in this, I mean, there is still some slope in this d of n. It is still n-dependent, even if your n is as large as more than 100,000 sites. But nevertheless is what we obtained. So it is essentially the calculation of this guy. And we calculated this guy, as I said, at a fixed n, as big as we could do with good statistics, and at different value of disorder. And so what happens is the following, that if disorder is bigger than 18 something, 18.2, 18.4, then this guy is, I mean, this average is almost independent of the system size, and we clearly have a localized situation. So the localization transition is well identified. So there's no doubt that it is somewhere here with some between 18.2 and 18.6. And then if we go to smaller disorder, then we have an apparent, I'm stressing, an apparent situation where your fractal dimension is not 0 and it is not 1, because 0 it is localized situation, 1 when it is ergodic. So it is something in between. Again, if you increase size further, then this point would go up. And one can see that the convergence is not reached. So this guy does depend on n. So we cannot say that this is already an asymptotic result. And this is again limitation of the numerical exact diagonalization, and we can only say, well, it is likely that here there is a non-ergodic phase and extended. But then other guys come and say, well, look, we don't believe, because possibly you need sizes of the universe in order to see that this point go up, 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 and then will be 1. And this point also will raise up to 1, and then so this is all the transient situation. But here there is one very important point which I want to stress, and we found it and studied very carefully, and it was a surprise for us. The surprise was the following. Look what happens. So here there is a smooth behavior of these points. But at some point which corresponds disorder approximately equal to 10, this means approximately 2 times smaller than the one of the localization transition, you have a jump. So it is the jump not exactly to 1. It is a jump which is sort of halfway from this point to 1. And as I said, it is still n-dependent. Therefore, both these points and these points will go up for sure. How long, we don't know. How far, we don't know. But there is a very sharp jump. And this jump tells you that something is happening at w equal 10. And something, what happens is a sharp, like first order transition. And this is the blown up area. And you see that this jump is well seen both in the fractal dimension d2 and also in the fractal dimension d1, which contains psi to the squared, and in order to escape normalization, there is a logarithm here. So it is essentially the Shannon entropy. And there is also a jump here, but it is not. It is much smaller and not so so well seen. Then it is a very recent. This is published in our PRL of 2016. But this is a result which is unpublished yet. So this is a completely different quantity, which is a Green function. A Green's function on this random regular graph at coincident points. So you just take the Hamiltonian and invert it like a matrix, and then study the imaginary part of the Green function. Imaginary part. And imaginary part comes from the very small imaginary part of the level of machine smallest number. You put it there, and then, as we know from Anderson, I don't have time now to discuss it, the first criterion of delocalization that has been suggested by Anderson in his first work was the following. You add a bit of imaginary part in your energy, and then when your system size goes to infinity, this imaginary part blows up and becomes independent of the bare imaginary part that you put. And if that happens, this is a extended phase. And this is sort of spontaneous symmetry breaking, if you wish. So you add an infinitesimal imaginary part, and the imaginary part of the Green's function become finite. So we have studied this imaginary part. How does it behave as a function of disorder? And what we have found again a jump in this imaginary path. And here you see a very careful evaluation of the error bars. And here it was not so easy to evaluate the error bars, but here we did it with very high precision. And in order to make sure that we really deal with some real effect, we took not so big systems, so the jump was small. The jump actually grows when the system size grows, so as it's seen here. And here we intentionally took not so big system, but we took huge statistics of 50,000, normally 50,000 realizations for each point. And each one 20,000 matrix, 20,000 by 20,000. So you, this was a 1 year of computation on a cluster machine. And so what we see again a jump, and this jump happens again close to W equal 10. And moreover, the position of the jump is incredibly sharp. But the position of the jump is slightly dependent on the size of the system. But this is a well-known effect. So when people studied Anderson localization, so the first value for the Anderson transition was 17.5. And then as machine become more and more powerful, people were able to make the organization of bigger and bigger system. At the moment, it is 18.6, I would say. So the transition point, the apparent transition point, even for the well-studied Anderson transition, it somehow evolves and becomes evolves in the direction of larger disorder as system size increases. And here you see what happens. Here it evolves in the direction of smaller disorder, because this is 10,000, this is 20,000, it is 10.2. And here for 128,000, it is in between of 10 and 9.9. We did not do better resolution. So clearly, what we see sort of transition. This transition is first order, and it is tempting to associate it with the ergodic transition, because if all this smooth curve would be just a finite size effect, as some people still argue, that you go to astronomic sizes and everything goes to 1, I object, saying, well, if it is just finite size effect, what the hell is such a sharp jump at some point? So I would say that this jump is a marker of some transition. What is exactly the nature of this transition? Is it already an ultimate transition to the ergodic phase, or it is some more complicated thing? We currently do not know. So just 1 minute about the widespread nature of multifractality. So this is a work which is barely related with what I'm talking about now. This is the following thing. This is the multifractal analysis of the work done in a driven two-level system. So we have a two-level system which is realized like a Cooper pair box, like quantum dot with superconducting in a superconducting state, and you drive it, and this is an experimental plot, and you study, you drive it many times back and forth, and you have statistics of work which is done by your external source, and then you analyze this statistics of work using exactly the same multifractal distribution function, and what you find the following. You find this f of alpha, and you find that the shape of f of alpha depends on how fast are you driving. So if you drive very slowly, then you must, this is a theoretical curve, this is an experimental curve, and this is random matrix. So if you drive it very slowly, then your work should be always equal to the difference in the free energy. And so the distribution is very narrow, and it is like the ergodic state. As you increase the speed of drive, then your spread becomes bigger and bigger, and your shape changes. Here the shape is almost parabolic. But when you drive very slowly, then you develop a slope, and it is essentially the beginning of this slope, which is linear one. So you obtain a linear piece with some cutoff. So it is still not localized case in this language, but you see the following thing. You see that this multifractal analysis is very useful also for things like distribution of work, and this is in fact the generalization of Yerginsky equality, because Yerginsky equality on this language is nothing but the normalization of the wave function. You may study not only the average like Yerginsky equality, you can study moments of it, and the moments of the same nature where the logarithm of psi is replaced by work. So what we have shown that the distribution function of work has this form. Here stays the work, here stays the work, and instead of logarithm of n, there is a big number which is characterize your two-level system. And now, this is just to say that experiment and then theory for driven two-level system, which is a classical theory, is a matter of fact. And the results that you may get from certain type of random banded matrices where there are also multifractal states, they actually resemble each other very well. So it means that random matrix is a very good system-independent language to address this multifractality phenomenon. And so I come to random matrices. So what I'm going to do now is not to study this generalization of beta lattice like random regular graph, which is in fact a toy model for many body localization, as we think. We will be studying now the toy model for the toy model. So, you know, the real model is many body localization. The toy model for that is random regular graph with single body localization. And toy model for this random regular graph is this random matrix. And what is this random matrix? This is the simplest deformation of celebrated Wigner and Dyson random matrix. So what is Wigner-Dyson random matrix? It is a matrix which is Hermitian and with zero average. Every matrix element has zero average, and with some variance which is equal to all the elements. So all the elements fluctuate with the same variance and around zero. This is Wigner-Dyson matrix. Now, suppose, and this was actually the old results of people like Uzi Smilansky in his group, that if you take a clean random regular graph without disorder, but as I said, you can connect sites in plenty of the ways. So you have a big ensemble of random regular graphs with the same connectivity and with the same number of the points. And then you can compute spectrum, you can study this spectrum, average over this ensemble. And what you find that with the accuracy that was, let's say, 20 years ago, when Uzi Smilyansky and his group studied this, with this accuracy, it was Wigner-Dyson. So the distribution was Wigner-Dyson. And then I say, well, if for this reason or the other, this random regular graph, clean, gives you Wigner-Dyson distribution, Wigner-Dyson ensemble, then the disordered one is just to add some fluctuations on the diagonal, because what is disorder? Add some extra fluctuations on the diagonal. And so we come, heuristically, we come to this very simple generalization of the Wigner-Dyson random matrix. So instead of saying that the variance is everywhere the same, we say that it is bigger on the diagonal. So we say that on the diagonal it is, let's say, 1, the variance, and off-diagonal elements have variance which is parametrically small and parameterized by the system size. Why parameterized by the system size? Because there are n diagonal elements and n squared of diagonal elements. Therefore, in order for small off-diagonal elements to do something, they should be, I mean, for the off-diagonal elements to do something, they should be small because they are more numerous. And so we define such a generalized Rosenzweig-Porter ensemble. And in fact, this ensemble with a special diagonal was put forward by Rosenzweig and Porter in 1960. So it is already more than almost 70 years around. And then in the 90s, people studied this type of generalization where there is the variance which scales with the system size. And it was found that there is an Anderson transition on that model, and people like Edouard Brezin, Hikami were involved in this study. Yet they overlooked that there is the second transition, and this is what we did quite recently. And I give you only the result, and this is the result of for this f of alpha, because this is the best language to say what is going on. So, as I said, there is a control parameter gamma here. So when gamma is smaller than 1, then there is this degenerate form which signals of ergodicity, ergodic delocalization. When gamma is larger than 2, when gamma is equal or larger than 2, then you have the situation where f of 0 is equal to 0. In some weird way here, but it is equal to 0. And this means that it is localization. This corresponds to localization. Gamma equal to 2 corresponds to the Anderson transition point. It is just a continuous deformation from this localized situation to this. So this point goes up, 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 and eventually this peak disappears, and this is the critical point. But the critical point of the Anderson transition is not distinguishable from localization, because f of alpha equal to 0 is equal to 0. But what we have found specifically is that in between of 1 and 2, there is a non-trivial form of this f of alpha, such that you have a gap here on one hand, and this gap is signals of a delocalization. On the other hand, you have a finite spread, and this finite spread is from 2 minus gamma to gamma, so that when gamma approaches 1, these two lines collapse in 1, and I have this situation. And this was indeed a discovery of the second transition in such simple random matrix model. The second transition means that you here have extended but non-ergodic situation, and as gamma becomes smaller than 1, you have ergodic one. So at gamma equal 1, you have ergodic transition. So basically you have, this is the definition of the ensemble, and this is the phase diagram. So at gamma greater than 1, I have fractal dimension equal to 0. Then they behave linear here. This is an analytical result. So all what I'm talking about for this random matrix ensemble, it is an analytical result. It is not just, of course it has some numeric support, but it is an analytical result. So there is a linear behavior. And this is this non-ergodic extended phase where the fractal dimension is between 1 and 0. And then, when gamma is smaller than 1, I have fractal dimension exactly equal to 1, and this is the ergodic situation. And this is Anderson transition, this is an ergodic transition. What actually is special for this model is that it is not, the multifractality is simplest possible. This means that the fractal dimension, which generally depends on Q, is actually independent of Q for all Q greater than 1/2. So therefore I did not put here any index. It is equal to this 2 minus gamma. So as I said, this was the result of our paper, and then very recently mathematicians from, it's clear mathematicians, they prove theorems, they do not do numerics, they do not do pictures like I do. They prove theorems, and they proved it on the level of the theorem that all our results are correct. Now, okay. Now, since we now have some specific situation where this search was successful, I mean the search for this situation where there are 3 phases. So this was my initial search. So we have found such situation in a random matrix ensemble, and very simple one, and the one which is around for 60 years. So now, of course, it is interesting to see also by analytical means how things are going on that ensemble. And the first thing we looked at was the return probability. So you put a particle on one side, and then you see what happens with time. So of course there is also a spread here, but we were interested in the local quantity where there is only one side involved, and everything depends only on the time. So it is just return or survival probability. So what this is the result, and it has some specific features which are specific to this particular oversimplified case, but it is it has only also some generic features. And one of the generic features which is very important is the following: that as time goes to infinity, as time goes to infinity, your return probability is not 1 over n, so there is no equipartition over all the sides. So it doesn't spread over all the sides. Instead, it behaves like 1 over n to the power d, where d is fractal dimension. And you see that if you take different sizes of the system, different by a factor of 2, you have equally spaced asymptotic values here, and they correspond to that value. This is already non-ergodicity, because in the ergodic situation you put a particle in a point, and then at very long time it is spread over entire system. Here it spreads only over the part of the system, over the fractal part of the system. And then there is the initial behavior. And this initial behavior is simple exponential. This is an analytical result. This is also an analytical result, by the way. It is simple exponential. It is not stretch exponential. It is not power law. It is simple exponential as it would be in an ergodic system. But the difference is that the rate of this simple exponential scales like 1 over n to power 1 minus d. So it vanishes in the thermodynamic limit. So it is a simple exponential dynamics in a finite system. But it is slow dynamics because this rate is inversely proportional to 1 over n to some power. And this is the main feature of all such systems with of this non-ergodic extended phase. You know, in the localized phase, this guy stays constant. In the ergodic situation, it goes exponentially with the rate which doesn't depend on the system size. It's some microscopic rate. In this situation, it shares both. So it goes like a simple exponential, but it goes with the anomalously small rate. No, there is a microscopic time here, of course. This is quadratic behavior in a microscopic time. I'm not interested here in the microscopic. Parameter is system width of the spectrum. Width of this it's width of the spectrum. So the inverse width of the spectrum is the characteristic time here. Okay, I'm sorry, I don't have more time to discuss it. And this is the global picture, which is in the full logarithmic scale. This is semi-logarithmic scale, and this is full logarithmic scale. So what you see is also something which is generic in such situations. So you see that there is overshooting here. And there are 2 times here. The first time is where this exponential behavior fails. So the deviation becomes large from the exponential behavior. And this time is 1 over gamma logarithm n. And gamma is this, which is power law in n. So one would think that this is the exceeding of the accuracy, but this is an analytic result. And then there is another time which is just Heisenberg time, which is equal to n, I mean proportional to n. It is 1 over mean level spacing. And in between there is an overshooting. So this thing is a feature of all these systems. And now, if you allow me, okay, 5 minutes. This is an important thing. This is, again, a generic feature of this non-ergodic extended phase. So using this example, which is analytically solvable, I just identify features which have wider implication. So first thing is the local density of states. So the local density of states is the sum over all states, delta of energy minus eigenstate energy. And if this psi squared would be absent, that would be a global density of states. So it just counts the energy levels. But local density of states is such that this in front of the delta function there is a weight, and this weight is psi squared for this state at a given point. And so what happens with the local density of states is the following, and this is also an analytical result for this model. A typical local density of states. So I am at some point. What I see in this point, I see in this this point belongs to some fractal support, which I told you about last time. There is a stratification of the space. So this point belongs to some fractal support. Now, there are N to D states which live on this fractal support. We share this fractal support. And all of them have high amplitude at this point because they are made of the linear combination of one and the same functions on the particular sides of this support. So they have high amplitudes, and the amplitude's height psi squared is n to minus d. It is much bigger than on the average, or the average is 1 over n. And then there are, what you can also see here, you see the tails of the wave functions which live on the other support. And those amplitudes are parametrically small. They are n to minus 2 plus d. So this is bigger than 1 over n, and this is smaller than 1 over n. And so there is a parametric gap between the two. So the width of this region of big amplitudes, of big weights, is exactly that gamma that I have been talking about. And it is the mean level spacing, which is a global mean level spacing, times the number of states here, times the number of states living on one fractal support. And so what we see that in the local spectrum there is a mini gap. Mini because the width of this, the mini band, sorry, not mini gap, mini band. It is mini band because the width of this guy is vanishing in the thermodynamic limit. Yet it contains infinite number of levels in the thermodynamic limit. So this is a band, and this is a mini band. And then what happens if I change the point of observation, then this mini band is shifted to another position. And then if I take into account all possible points or all possible fractal supports, they of course pave the entire energy space, and that would be the global density of states. What is important, this is not a proof, but what is important, and we believe that for generic case, such as more generic case is what happens on random regular graph, this mini band is not just made of states with high amplitude and the spacing which is more or less like the global one. The mini band in the generic case should have some fractal structure, so that the counting function is like this. So there are big gaps, there are small gaps, so there is some distribution of the gaps. And this is not proven yet, but I think that this is the case. There are many reasons for that, but it goes, I am running out of time. I wanted to tell you the difference between the local and the global spectrum. Some people asked me about. And then, in the end, I show you another example, very recent work by Deng, Reis, Shlyapnikov, and the others. And they studied this situation where disorder was not a real disorder, but so to say Aubry-Andre disorder. So it is two incommensurate frequencies. So it was just strongly correlated disorder, which was used in experiment like a real one. And this work shows you two things: that it is very dangerous to use Aubry-Andre instead of real disorder, and secondly, that there is in this system there is transition from multifractal states to extended states, so they see the transition very clearly. If somebody wants me to tell more, this, in my opinion, this is a beautiful numerical work, And if one wants to speak about that, I can speak more. I can also speak about this spectrum, continuous, absolutely continuous, singular continuous, and so on. But I have to finish, and this is basically the conclusion. And the main conclusion is that there is good reason to have this third state on the random regular graph. And therefore, there is good reason to believe that it is also in the many-body system. And then there is a system, very simple, random matrix, in which everything is proven, in which you can extract characteristic features, and then you can compare these features with, at least you have some roadmap, what is compared with what. And you have one very solid case where such third phase exists in this random matrix situation. And as I said, there is an interesting direction to study this also analytically for Aubry-Andre disorder, where this is very well seen. So there is some topological aspect of this problem in this situation, but I'm sorry for.